There we go. So my name is Kristine Boykin, and I'm with the University of Reading, with my supervisors, John Methvin and Tom Frame, and Nigel Roberts and Stephen Mosley from the Met Office. And today I'm going to be talking to you about my PhD project and how it kind of fits into the value chain, extracting likely scenarios from high-resolution forecasts in real time. So the first thing I'll do is I'm going to go into a little bit of the motivations of what the project is about, and then a brief overview of the methodology, and then kind of get into the nitty-gritty and how it's designed to sort of help forecasters in the future to help better predict and output forecasts for like high-impact weather, for example. So forecasters right now, when they are looking to make a forecast, they're going through a huge amount of really complicated data. There's lots of variables. They've got different ensembles like MOGREPS G and MOGREPS UK at the Met Office. And that data is constantly being updated, hourly in some cases, daily in others. And forecasters have very limited amount of time to sort of process this information and to come up with related weather forecasts. And this is even more critical when it comes to high impact situations where things can change very rapidly, and speed and accuracy to deliver those warnings and impacts to the end users is even greater. So this project aims to find out, is there a way that we can actually extract maybe a few scenarios out of an ensemble instead of having to look at, say, 18 plus different members in order to see what your options are in terms of a weather event? And if we find these scenarios and maybe cluster members around them, is there a single member that stands out as being sort of a representation? And then we want to know how these sort of evolve through time, through the forecast itself, through multiple forecasts. And then what kind of events and variables can our method eventually be applied to? So the methodology, we're starting with MOGREPS UK with the idea that looking at a global ensemble, you'll have smoother fields. It's a little easier to cluster to start with. And then we're eventually going to move our method to look at MOGREPS UK data. We're looking at a large domain size to start with. So we can really see large weather events maybe moving in over the entire forecast period, which in this case is about 8 days. We've chosen the wet bulb potential temperature at 850 hectopascals, and we're applying the gradient to sort of find the defining features, in this case, frontal regions. We're looking at the fraction skill score to define distances between members, and then we're taking this information and applying k-metoids to it to sort of cluster into anywhere from maybe 2 to 6 different clusters, or 2 to 6 different scenarios in this case. And then an algorithm is being applied that determines the optimal number of clusters or scenarios, and then which members best represent those scenarios. And then this, of course, will eventually be provided to forecasters and summary statistics and various plots for their analysis and probability of occurrence. So I'm going to walk you sort of through the process. So we're starting with the wet bulb potential temperature at 850 hectopascals, as I said. So this gets us above the boundary layer, and it's a nice smooth field. It's good to begin building a clustering methodology around. It's a good indication of where air mass boundaries are, and therefore corresponds to frontal regions with heavy rainfall very well. Now up at the top left corner, you can see this is our wet bulb potential temperature plot. So this is from a MOGREPS G forecast from the 6th of October, 2018. It's the control member 0. And at lead time T plus 117 hours. And you can see that there's a really nice boundary that's sort of building there. Now we apply a gradient to the field to find the frontal regions. And you can see in the top right-hand plot, we have sort of a front kind of standing out. This actually corresponds really well with the synoptic chart you can see down on the left, which is as close as I could get it to the lead time of T plus 117 hours of this particular forecast. But you can see there is indeed frontal regions that were moving really close to the UK at this point in time. This is actually Storm Callum, if anyone happens to remember that, where we had some flooding events that occurred with that. Now, this is really just getting it started, of course. The next thing we want to do is we want to be able to apply the fraction skill score. Now, in order to get it to that stage, we need to convert the field into a binary. Now, this is because a gradient field has a lot of fine scale features that tend to make clustering rather difficult. And we want to sort of eliminate that and make clustering easy enough that we can really group members based on primary features like this frontal region. Now, the fraction scale score, some of you may already be familiar with. It's a neighborhood verification method, and it focuses on domain-wide agreement instead of a point-by-point agreement, which helps reduce the double penalty effect. And you can actually take the fraction skill score between two different ensemble members and determine an actual spatial difference between them, approximately. Now, this information, once we have the fraction skill score distances between members, can be have k-metoids applied to it, rather, to sort of cluster members together. And some of you may already be familiar with k-means clustering in particular. That one's very commonly in the meteorology fields. But k-means actually takes the members and creates a mean out of the members as a center point. And in this case, because we're dealing particularly with high impact situations, we don't really want to have a mean, as it would smooth out the field and you would lose a lot of fine scale feature in the ultimate forecast that's presented as a scenario, which could be relevant to where, say, higher impact may be for a forecast. So in this case, we focus on k-metoids, which actually uses a member as the center instead. Now, the method that we use finds a window of interest. So essentially, this is when you've reached a point in a forecast where the members have moved away from one another after the perturbations in the beginning, and the forecast itself has now reached a stage of low predictability, but high clustering. So you start to see members really grouping together. So the algorithm finds where in the forecast this window of interest sort of begins for the clustering, and then looks at the different clusters to find the optimal number, somewhere between 2 and 6, and then chooses a member that's representative of those clusters. Now, this bottom right-hand plot, this is just an example of two members that have been clustered together in this situation. So you can see member 0 and member 2 are very similar in terms of their frontal structure. But we don't really want to just look at one. We want to sort of look at everything and see how the members are grouping together. Now, right now, this is just a brief example of what a forecaster may be looking at on one particular screen for one particular variable, in this case, a binary field of the gradient of the wet bulb potential temperature. This is 18 different members. And just glancing over them, you can see some of the members are a bit more standout than the others in terms of the shape of the frontal region, and they might cluster together in different ways. So we want to be able to take this and really reduce it down to provide forecasters of a few instead of 18, right? So this is the next stage of what this looks like. So we've clustered these members together. Now each member is its own color. So you can see there's 18 different colors on this chart. And you can see in the top titles of the subplots, the R representative, so it's the member as the representation of this particular scenario and this grouping of members. And then which members within the ensemble have ended up in that particular cluster. And the top 3 are actually very well clustered. You can see that they line up fairly well. The fronts are all in roughly the same region. The bottom left cluster has about 2 outliers in it instead of really matching up. But that's actually quite useful. We can see these 2 members individually if we need to look in to find out if there's outliers, for example. Now, this is a rather complicated plot to really just be able to look at and glance to. So we want to take these representative members and actually present them to our forecasters as 4 separate scenarios. Now, this is the wet bulb potential temperature with the mean sea level pressure overlaid on top. And you can see as we get closer to T plus 117 hours in just a moment, 4 different scenarios have really started to appear with these 2 different storms sort of moving through. So this is more what we're aiming for to give to our forecasters so that they can then take this and apply probabilities of each of these 4 events and be able to work out as lead times get closer, which one is the more likely to occur. Now, this, of course, is just one forecast that I'm showing you. But we've actually applied this to several months, and this is just an example here of October 2018, some summary statistics. Now, the y-axis for the top two plots is the lead time in hours, and the bottom is the x-axis is the start time in days, and the bottom plot is the number of clusters. The top plot is actually our ensemble spread of the members now and the forecasts. Now, of course, as you would expect, when you're starting at a lead time of 0, the ensemble spread is very, very low because all of the members have only just been perturbed from the control member. And as we move further out, the ensemble spread increases. Now, you can already see in the ensemble spread that there's sort of a diagonal trend to some of the sections. The dashed lines, the dashed gray lines that are diagonal, are actually across valid times. So they're every 24 hours you'll see these dashed gray lines. And then the dotted vertical lines are just every 7 days for ease of reading the plot, really. But if we move down to the second plot, so this is the sum of the distances between the members in a cluster and their medoid, which is what the center of a k-medoids cluster is called, and it's been normalized. You can still see these diagonal trends, but the red line is actually where the algorithm has picked out our window of interest, the start time, which is set for 48 hours. So you can see there's a little arrow down at the bottom of that second plot and Storm Callum written next to it. That's roughly when Storm Callum started to impact the UK. And you can see, following up that valid time gray dashed line, the window has been picking out across that valid time about when it needs to start looking at the clustering for me. So this is quite interesting. And it's showing that when we have low predictability, so when the distances between the members and medoids are spreading out, and the ensemble spread has increased, when there's low predictability, we're actually getting very strong clustering, which is quite interesting and useful information. So I'm just going to go over a summary of what the method is really quickly, and a few conclusions that we've been able to come up with, and then I'll open up for questions. So our method, we're using the fraction skill score on variable fields, in this case, the wet bulb potential temperature converted to a gradient field, to define distances between ensemble members, which we're then applying the k-medoids to in order to group them into clusters. And then the algorithm that I've developed is choosing an optimal number of clusters between 6, and then choosing a representative member out of those clusters that best represents the scenario that we can then present to our forecasters. Some of the conclusions we've already been able to draw from the work. We have strong clustering occurring when predictability is low. We've been able to extract a few significant scenarios from our ensemble forecasts, and we have been able to extract representative members that accurately represent these scenarios in sort of a center point. And that is the end of my presentation, and if I'm open to any questions.
Thanks, Chris. Very